Hello everyone, thank you for coming to my presentation. My name is Xishun Zhang. I'm a PhD student from Auditory Prestige School, Hanover Medical School, and also co-star of Excellent Hearing for All. Today, I want to introduce our work about neural health and activation in the human auditory periphery, insight from the computational model for cochlear implant and auditory nerve implant simulations. Quick recall of cochlear implant, or CI. Those are hearing loss treatment devices who restore the hearing ability from that person. As one of the most successful implants in the world, CI has successfully provided auditory perception to a person with served to profound hearing loss, and more than 1 million people had benefited from CI. Most of them obtained good speech perception and some enjoying the music. However, CI still faces some challenges. One of those challenges is called electrical nerve interface, with the aspect of the status of auditory nerve fibers, also called neural health. On the other hand, the stimulation of CI is not specifically because of a large voltage spread inside the cochlea, which also be a problem to influence the performance of CI. The success of CI is highly depends on the health and function of auditory nerve. Many studies has reported a significant decrease in neural response for degenerated fibers related to the age or pathological process, which like exploding a really loud noise or take some medicines. Unfortunately, we are currently unable to directly assess the neural health for auditory nerve fibers in vivo. To address those questions and challenges, we developed a computational model framework as shown as here. We believe such model could help us to understand the mechanisms of electrical stimulation with CI, and also this model could help us to predict the neural fiber excitation with different stimulation mode or even different implant to reduce the voltage spread. Furthermore, a computational model could be used to develop a neural health estimation methods like the different threshold between partial tripolar and monopolar simulations, or the response from the ECAP with different interface gap. Here is a general look about our models. Our model is created based on histological human cochlear data with a commercial CI insert into the scalar tympani. And a realistic auditory nerve fiber geometry with 30,000 fibers was incorporated in this study, covering a frequency range from 20 Hz to 20 kHz to match the normal hearing range. Each fiber was defined as a set of points represent compartment of these fibers, following the fiber morphology proposed by Kochman and his colleague. Each fiber was simulated in one of following three stages into 12 dead regions, like healthy, fully healthy fibers shrinked, the peripheral axon diameter reduced to 50%, or degenerated. This fiber lose their entire peripheral axons. The 12 dead region had impaired length of either 0.5 mm, 1.5 mm, or 5.0 mm, and they are spacing at an interval of 30 degrees along the organ cavity. Each simulation were considered only one impaired region each times. So with this computational model, the threshold level and ECAP response for different neural health conditions were estimated and evaluated because we hypothesize that the focused partial tripolar stimulations due to more focused stimulation is more sensitive to impair neural health conditions. And also, for the healthy auditory nerve fibers, we observe such an effect that if we increase the interface gap IPG, we will observe such a higher amplitude good function slope and also the lower ECAP threshold. And some study also claim that if the neural health turns too bad, such effect will be disappeared. For the first experiment of focus stimulations, when we compare the simulation result with the same simulation mode like monopolar only or partial tripolar simulation only, we observed that the T-level elevation was observed under impaired conditions, specifically with partial tripolar threshold showing greater sensitivity to neural health deflect than the monopolar threshold. Furthermore, if we compare the stimulation result between two stimulation modes like monopolar against partial tripolar, the maximum T-level differences, which is called delta T mode here, between monopolar and partial tripolar occurred consistently with the impaired condition across all dead regions, which seems to be a promising measurement of neural health status. For the ECAP experiment, the model builds up on the fact that each fiber contributes to the CAP response differently which based on the location of the stimulate electrode, recording electrode, as well as the neural health conditions. So in our models, the ECOG response is expressed as the convolution between peri-stimulus time histogram (PSTH) and single fiber cat contribution (SFCC). Both of them are affected by the neural health conditions. The ECOG waveform predict from those results closely resemble those clinical record human data waveform, and we also observe that if the nerve is degenerated totally, the ECOG response will be totally different. The ECOG experiment was performed with the monopolar simulation mode and the biphasic catholitic single pulse. Three interface gap was used in this study: 2 microsecond, 8 microsecond, and 40 microsecond. For the stimulate electrode, we use the current level from T level to M level to recording amplitude goods function, with the recording electrode 2 apical than the stimulate electrodes. However, the simulation results from the ECOP IPG slope and offset effect were not consistently associated with the neural health conditions. There are a lot of factors could influence result. In addition to the neural health estimation, our model could also be used to investigate stimulation through a new auditory prosthetic, so-called auditory nerve implant. Unlike CI, ANI is totally bypass the cochlea and directly stimulate fiber inside internal acoustic canal with a more specific stimulations, which is seen as a way to solve the voltage spread. So with our models, uh, we could estimate the threshold, dynamic range, and frequency specificity of ANI with respect to the commercial CIs to see the benefit of ANIs. Simulation results suggest that the ANI offer advantage over CI in terms of lower threshold, order electrodynamic range, and improved frequency specificity than CI. As a short summary from presentation, our simulation results suggest that the differences in threshold level with partial tripolar and monopolar simulation is a possible method for estimating neural health. And also comparing the different devices, A9 shows some benefit than CI in the frequency, specificity, threshold, and electrodynamic range. So in general, our model offer useful tools to investigate auditory nerve activation mechanisms. And also these tools could be used to further develop a fitting strategy, neural health estimation method, or predict a new implant performance. So I would like to thank you very much for your attention, and I'm looking forward to your questions.